And we are recording the meeting. Okay, great. So tonight we'll have a lot of fun talking about some theoretical topics in computer science. Computer science, like the term suggests, is a science. And engineering uses this science to accomplish the real-world goals, such as building Google Meet or building Google Docs or building the Google search engine. And also, other non-Google things, Microsoft Word, Microsoft Excel, and whatever else. But engineers use a theory to accomplish the engineering goals that they set out to accomplish. And the theory is the object, however, the theory is the object of an independent, somewhat independent discipline, which is the science part in computer science. So a computer scientist, as opposed to an engineer, is somebody whose job in life it is to better understand computer science and augment the knowledge, the body of knowledge that the world has about computers and how they work and how they can be used. So what we've seen in the last, since the beginning of the class, the first 10 lessons or so, is mainly applications. We've done a little bit of JavaScript. Well, the JavaScript that we did is part of engineering, but we have not presented the theory behind it. Today, I want to give you a glimpse of what theory there is behind computer science. My expectation here is not that you guys will be able to prove or disprove some of the open conjectures, some of the open questions in computer science, such as one that we will mention later today, which is whether P is equal to NP. And I will explain what that question even means. My expectation, however, is that a handful of you will hopefully get inspired by tonight's lesson and will get themselves into a computer science program to actually learn the science part of computer science, mainly, or potentially for the purpose of an academic career and potentially just for the purpose of becoming better computer engineers. Either way, I'm hoping to show you aspects of computers that you may not even ever have thought of, and inspire you to learn more about them. And I shall proceed by sharing my screen. Give me a sec. Preset now. Entire screen. This screen. Share. Okay. Do you guys see my screen? Computer science theory and conclusions?
Yeah.
Okay, great.
I don't see it. I see a black screen.
Huh.
I see it.
Oh, really? Others see it? Okay, go ahead.
Looks like I am actually presenting what I'm expecting to be presenting, so that seems fine.
I just see a purely black screen on my end, but that's okay. If everybody else can see it, go ahead.
I can unshare and try again. Let's do that. Present now. Your entire screen.
Suddenly I could see you just fine. But, yeah, now I see it.
Okay.
Now I see it. Yep.
Wonderful. Okay. No announcements, no plan for today. Let's start from the easy stuff. Let's start with quantum computers, because quantum computers are easy. Like, who doesn't understand quantum mechanics? I would expect everybody on this class, everybody on this call has a background in quantum mechanics, right?
Quick question.
Yes, please.
What's the definition of the word quantum?
Ha. Okay. That is actually a very good question.
Dean, that stuff.
That is actually a very good question. So quantum is a word that was introduced, to the best of my knowledge, by Einstein in the early 1900s. I want to say 1905. Don't quote me on the date. When he was studying one open question in physics. It was the photoelectric effect. Photoelectric effect is one of the problems that led to the development of quantum theory. The photoelectric effect relates to, or is the effect of a ray of light shining on a piece of metal, causing the surface of the metal to produce electrons. to sort of, the ray of light causes electrons to bounce off of the metal, and these electrons can be captured and their energy can be measured. And the energy values that could be measured from these electrons did not make any sense to the scientists of the early 1900s. There was no way that they could explain why the distribution of energy of these electrons was what it was. And Einstein reluctantly, he was not fond of quantum theory, but he reluctantly conceded that it had to be because the ray of light was made up of individual pieces of light that today we call photons, particles of light. And he called them at the time, 100 and change years ago, he called them quanta. And so he invented the term quantum to represent a bundle of energy, essentially. A little, a little speck of energy that's traveling in the form of light that can hit a metal and be absorbed by an electron. And then once the electron has absorbed that energy, it has a very specific amount of energy. So the term quantum refers to photons originally, but now we're talking about quanta in a broader perspective. There are other things that we've found in the world that bundle up energy and bundle up other physical quantities. I will not get into those quantities in too great detail, but bundle up these quantities into little discrete amounts. Okay, what quantities can be bundled up? Well, energies, like I said, momentum, angular momentum, and let's leave it at charge, electric charge, and let's leave it at that. Okay, so we've got these little bundles of physical quantities, and they have some very, very interesting properties that make them very interesting from the perspective of a computer scientist. You've heard about quantum computers in the news, and they're hailed like the second coming of Jesus. It's great that we have these quantum computers, but what are they really, and how do they work? I would like to give a very short presentation on quantum mechanics, just enough, hopefully just enough for you to understand a little bit of the language and understand what's so powerful about these things. First of all, and please stop me if what I'm saying doesn't make any sense to you. And I understand that, jumping on a call and learning, suddenly that it'll be about quantum mechanics could be a little challenging, from an emotional perspective. But hopefully, you will come out of this tonight without any PTSD. That's the goal. So let me just present the very, very basics of quantum mechanics, just enough for you to understand how a quantum bit works and how a quantum computer works. First of all, I need to introduce some symbols that we will use. This weird symbol with a vertical bar and a triangular parenthesis is a symbol for a quantum state. Okay, this is the quantum state X. Something, maybe a photon, maybe an electron, maybe an atom, something could be in this quantum state. Examples of quantum states. This would be a quantum state of a particle that points upwards. And this would be the quantum state of a particle, maybe an electron, that points downwards. What does up mean and what does down mean? I get to pick, right? I'm the scientist here. I set up my laboratory and I decide what is up and I decide what is down. But once I've decided what direction is up and what direction is down, a particle can either point up or it can point down. It can't point any other direction than the two directions that I'm identifying, because those are the two directions that I will be measuring the particle in. So when I look for a particle and I look for either up or down, I will find either up or down. Okay, so is this any different from regular physics? Well, in a regular physical situation, I can have, say, my little bottle of 5-hour energy. Where's my camera? Here. I can have my little bottle of 5-hour energy. It can be either pointing up or pointing down. There isn't anything magical here, right?
I'm kind of confused. Too much to process.
Well, try to follow. If you have a specific question, I can answer it. But so far, let's read the nomenclature. I'm using these strange parentheses to represent a quantum state. X is my quantum state. And I'm giving you as an example my little bottle. And I'm saying that this little bottle can either be pointing up or pointing down, right? And maybe it's pointing a little sideways, but if it's pointing a little sideways, and I'm only interested in whether it's up or down, I'll say, oh, this is kind of up. And this is predominantly down, right? So if I'm only looking at reality from a very, very coarse perspective, and I'm only looking at whether, it's up or down, sideways is okay, and it's going to be, I can still tell whether it's mostly down or mostly up, okay? So I can use my quantum mechanics symbols for my little bottle, but quantum mechanics allows me to do things that my bottle cannot do. For one thing, and this is where I need a little bit of fancy math, and it's not super fancy. The name is super fancy, but the reality of this is not super fancy. Quantum states are homogeneous of degree 1. What does this mean? It means that I can multiply a quantum state by any number, and the physics of that quantum state doesn't change. What does it mean? Say that, again, this is my quantum object, okay? Multiplying it by a number smaller than 1 is like moving it away from you. You see that it becomes smaller on the screen, right? If it becomes smaller on the screen, is it pointing anywhere other than what it was pointing before I moved it away from the camera?
No.
No, it was pointing up, and now it's still pointing up. What if I multiply it by a number bigger than 1? Now it becomes really, really big on the screen. Where's it pointing?
Up.
Still pointing up, right? So nothing really changed. I can make my state bigger or smaller by multiplying it by a constant, and the physics that's described by that state does not change at all, okay? That's an interesting observation. Now, this is where things get complicated, and this is where my bottle no longer allows me to represent a quantum state. In quantum mechanics, a state can be a combination of 2 or more states. And I'm representing a combination of 2 or more states, or 2 states, by using the plus sign, okay? So my thing, my quantum thing, is in a combination of an X state and a Y state. What does it mean that it's in a combination of a Y state and an X state? Well, maybe this means that it's both pointing up and to the right. Actually, no. Up and to the right would be something that my bottle could do. This is up and to the right, right? There's nothing quantum about this. What's magical about quantum things is that they can both point up and down. Can my bottle point both up and down at the same time? I'll give you the answer. No, it cannot, right? So my bottle is not a good example of a quantum system, at least not at this level of resolution and not with the kind of experimental devices that we have access to right now. But quantum things like electrons can both be pointing up and down at the same time. Now, if I measure them, if I actually go and measure whether it's pointing up or down, I will only find one of the 2 values. I will find up or I will find down. I will not find both. But before I measure, it can be both up and down. It's like an undecided bottle. Imagine my bottle is undecided. It's saying, well, I'm not sure whether I want to point up. Maybe I want to point down. I really don't know. Okay, then I come along and I ask it, so now, dear bottle, where are you pointing for real? And it's still undecided. And then it says, well, all right, I'll point up. Okay. And then the next time I redo the experiment, it'll still be undecided. I ask, so where do you want to point? Still up. And the third time, I'll go and ask, so bottle, where are you pointing? This time I'll be pointing down. Okay. So when we have a quantum state, we really just have a measure of the probability of getting a certain result from an experiment. If I say that my bottle, or my electron more realistically, is in a superposition of up and down without any scaling factor, I'm basically saying there's a 50-50 chance that it'll be either up or down.
So
when I measure it. Go ahead.
When you measure a quantum state, it's not like decided fully, it's just like a probability of what will happen?
Before I measure it, it's just a probability.
Okay.
After I measure it, it's like, you know, the lotto. The lotto is a certain number of numbers. I don't know if it's like 60 numbers or 90 numbers or something like that. Before the night when the lotto numbers are extracted, there's a probability that any one of those numbers will be extracted. But after the lotto, you know, after the lottery happens, then we know for sure what the numbers are. Okay, so something changes between the time right before the lotto happens and right after the lotto happens. That change is like what I was showing earlier, right? It's the change of my bottle deciding which way it's pointing. Before I ask it, which way are you pointing, it can be undecided. But once I ask it, so which way are you pointing for real, it has to make up its mind. It's either up or down. Okay, so this is very, very strange, because in regular physics, let's call it Newtonian physics, when I see a state and I measure it, I get the same result, right, every time. If this is my Newtonian experimental thing, and I look at it and I measure it, and I measure the direction of the cap, it's up. And then I redo the experiment, well, it's still up. And then it's still up, you know, it's always up. And I can measure it however many times I want. Nothing is changing about my bottle. I can make measurements about my bottle without changing the bottle. But in quantum mechanics, I cannot make a measurement without changing the thing I'm measuring. Why? Because before the measurement, the thing that I'm measuring is undecided. But because I'm measuring it, it has to make up its mind. It has to be either up or down. It has to be either left or right. It has to be in a very specific state after I measure it. Okay, this is weird. This is not normal. This is not what we expect from our physics classes in high school. Now, let's start talking about quantum computers. Well, quantum computers are things that have a bunch of quantum states. Is it like Schrodinger? Schrodinger is one of the scientists that invented quantum mechanics. He came relatively late in the game. A lot of the foundational work had already been done, but quantum mechanics at Schrodinger's time lacked a full theory of how it worked. And he provided that full theory by providing the Schrodinger equation, which is the heart of quantum mechanics. But the Schrodinger equation builds up on a lot of other people's work, including Einstein.
Theory?
What's that?
What's the full theory, like in summary?
What is Schrodinger's equation? I don't have it handy. Schrodinger equation. I think we're getting a little too far here, but I will show it to you at the very least. So a quantum state is represented by a function called psi. Okay, that's our quantum state. And it's a function of time and it's a function of location. So here it's represented as a function of time, but it's really a function of x, y, z, and t. It's a function of anywhere in the world at any point in time. We're looking at the quantum state of one thing, okay? So one electron has a quantum state that depends on position, anywhere in the world, anywhere in the universe, and any point in the history of the universe, any value of t in the history of the universe. So this is a partial differential equation, or actually it's a differential equation the way it's written here, because it's an ordinary differential equation because it's only relating to time. But in reality, it's a partial differential equation because psi is actually a function of x, y, and z as well. And it's showing us that the derivative with respect to time of the quantum state, and I don't know if you guys have studied derivatives, basically it's the rate of change of the quantum state multiplied by some number is equal to an operator called the Hamiltonian, which transforms that state. And the Hamiltonian characterizes the physics of one particular experiment. So, you know, we can talk about the Hamiltonian of electromagnetism. We can talk about the Hamiltonian of a vibrating, of an oscillator. We can talk about the Hamiltonian of an atom. You know, every physical system has a Hamiltonian. The Hamiltonian captures the physics of that thing. And once we have the Hamiltonian, the complete history of the quantum state of that thing is described by applying the Hamiltonian to the quantum state. The Hamiltonian applied to the quantum state gives us a derivative of the state, plus or minus, with some numbers multiplied to it. So
yeah, that makes kind of sense.
I mean, you are a very, very smart person. If this makes sense to you, you know, based on 10 minutes of explanation from me, you are probably ready for a brilliant career in theoretical physics.
Like, very little sense, but still.
Okay. But anyway, so this takes us a little bit far from where I wanted to be. So quantum computers have a bunch of quantum states. For instance, they have an array of, say, I don't know, 20 electrons or 30 atoms or 50, I don't know, 50 photons, you know, 50 things or some number of things, each of which is in a quantum state. And so we have lots of different quantum states. For instance, let's say that we have a quantum computer made up of electrons. We'll have the quantum state of the first electron, the quantum state of the second electron, the quantum state of the third electron, and so on. Okay? Now, why is that interesting? Well, I have to get there. So I told you that a quantum thing can be in a superposition of states. I showed you the example of, you know, my quantum bottle being undecided between being up and being down. Okay? So that's a quantum superposition. The most general quantum superposition is where we multiply the two possibilities, up and down, by two numbers. I'm multiplying up by h for some number h, and I'm multiplying down by k for some number k. So now I have a bottle that is h times up and k times down. Okay, and we talked about the fact that what this really means is probabilities of being up and down. Turns out that in quantum mechanics, the probability is really proportional to the square of the number. So h times up plus k times down really means that there's a probability of being up h squared times, and there's a probability of being down k squared times. Okay, this is a little you know, it's not entirely exact. If you actually go on to study quantum mechanics in college, you'll get a slightly different version of that, but hopefully this is understandable. Now let's say that we have a quantum computer made up of 2 qubits. Okay, 2 bits, 2 electrons. And each electron is in a superposition of states. So I've got my electron 1 that is in a superposition of up and down, and it's a times up and b times down. Okay, and that means that there's an a squared probability that it's up and a b squared probability that it's down. So far, so good. I also have my second electron. It's c times up and d times down, which means that the probability that the second electron is up is going to be something along the lines of c squared. The probability that it's down is d squared. Okay.
If you replace it with numbers, would it be a little easier to understand it, or is it more easy to understand using variables?
Well, I need the variables for the next step, which is to show entanglement. Entanglement is where quantum mechanics becomes like magic, you know, Dungeons and Dragons level magic, where really weird things start happening. And I need the variables to show you that that can only happen with quantum mechanics. And I obviously cannot represent the electron as a number. The electron is not a number. The electron is a psi wave function from our perspective, and I'm just super simplifying and saying it's just an up electron, and it's also at the same time a down electron. And similarly, my second electron is an up electron and a down electron with some, you know, with some scaling factors, A, B, C, and D. Now, like I said, I need the scaling factors, and you'll see why. Now, you guys know about the distributive property of multiplication, right? You do. Can you help me do apply the distributive property to this multiplication? How do I do that? Well, I have to take this term times this term, and then I have to take this term times this term, and then this term times this term, and then this term times this term. Right? Easy enough. So what do we get? We get AC times E1 up times E2 up. Okay? Then we get AD E1 up, E2 down. AD E1 up, E2 down. Then we get BC E1 down, E2 up, BC E1 down, E2 up. And then we get BD E1 down, E2 down. Okay, this is what we get. I'm just using the distributive property of multiplication, right? Anybody past probably, I don't know, 4th grade, 5th grade, 3rd grade can do this. Now, they would have numbers instead of wave functions and quantum states, but distributive property is just a distributive property. So, have we proven anything really interesting here? Well, there is something interesting here, but I need to show you something else first. Let me create a new quantum state. Now, let me say that this quantum state is a very, very simple state. It's a superposition of E1 up, E1 down, or sorry, E1 up, E2 up, and E1 down, E2 down. And I'm multiplying both by 1. Okay, 1 times 1 times. Okay, so the coefficients are 1. Okay, now I can take my formula from earlier, put it here, and see whether the two formulas work out, you know. Here I have E1 up, E2 up, and my coefficient is 1. So what is AC? AC is 1, right? It's E2 up, E1 up, E2 up, and the coefficient is 1. What's AD? Well, AD is the coefficient of E1, E2.
Is it 2?
E1, no, look at this. It's E1 up, which I have, and E2 down. But I don't have E1 up with E2 down. So what's my coefficient here? I don't have this, right? E1 up, E2 down does not appear here. So in order to make it disappear, I need to multiply it by 0.
Yeah, that makes sense.
And look at this. E2, E1 down, E2 up. I don't have it here. So what do I need to multiply it by?
0.
0. And what do I need to multiply E1 down, E2 down by?
1.
1. Okay, well, cool. I mean, we can do some math. That's all very nice and dandy. But the problem is that this doesn't make sense. Now, you may not have noticed this, but we set 4 equations. We said, so this was originally like this. Okay, let me copy it again. So we have created 4 equations, whether or not we noticed. The equation AC is equal, oh, come on. AC is equal to 1. And then we have AD is equal to 0. And then we have BC, oh gosh. BC is equal to 0. And then we have BD is equal to 1. Now, can we actually solve these 4 equations? Do these 4 equations have a solution? Well, let's think about it. Let's look at this one. AD is equal to 0. So some of you guys have been through some kind of algebra class, right? What does a d equals 0 mean? What are the two solutions of this equation?
Come on, algebra people.
I've seen some participants on this class that have been through enough algebra to tell me what the solution of AD is equal to 0 is, or it's R. There's two solutions.
Yep.
Okay, I'm assuming everybody is very shy.
Quick question, is this quadratics and roots?
No,
No.
we're looking for the roots of a system of four equations.
Okay.
These equations are not quadratics. They're, well, yeah, sort of, but you don't use the quadratic formula here. It's super simple, right? You have the product of two things. When the product of two things is equal to 0, it can only mean that one of the two is equal to 0.
Oh, yeah.
Okay, so this means that either A is equal to 0 or D is equal to 0.
And then would
Okay.
the other one just be any random number?
And the other one can be anything. As long as one of the two is 0, we're happy. And here we have either B is equal to 0 or C is equal to 0. But this doesn't make sense, because if A is 0, then this cannot be 1. All right, so A is not 0. So if A is not 0, then D has to be 0. But if D is 0, this cannot be 1. So this equation cannot go together with these other two. And this one also. If B is equal to 0, then this cannot be 1. And if C is equal to 0, then this cannot be 1. So this is a very special state. This is a magical state. Okay, this is a Dungeons and Dragons level magical state. Okay, this is a magical state that I cannot get by looking at my two electrons one at a time. I cannot say, well, yeah, I've got two electrons, so obviously I have a quantum state for the combination of the two, but the quantum state for the combination of the two is really just the description of one and the description of the other. No. This is an entangled state. It means that I cannot describe one electron. I can only describe the two together, because I cannot break down this entangled state into my two separate qubits. I cannot break it down into a state for the first electron and a state for the second electron. I can't do that, right? This state does not exist as two separate electrons. This state only exists as, it's a two electron state, but it's two electrons that are tightly intertwined in a way where I cannot describe one of them without the other. I cannot talk about the probabilities of one without talking about the probabilities of the other. This is the incredible power of quantum computers. They have entangled states. Entangled states mean that, say that I have, say, I don't know, 60 of these entangled electrons. I can measure my 64 electrons, and they can point up or they can point down, but they are tightly connected. The measurements that I'm making are on a state where all the 60 electrons are working together in a way that cannot be described through a quantum state for each one of the 60 electrons. Okay, so why is that important? If I have two qubits, okay, two electrons, and they can either be pointing up or down, how many different results can I get when I measure their direction? And I can either get up, up, or down, down, or up, down, or down, up. I've got 4 possible combinations. Okay. If I have 3 electrons, I have 8 possible combinations. If I have 4 electrons, I have 16 possible combinations, and so on. The number of combinations increases dramatically. That becomes tremendously important now, because with entanglement, if I'm able to entangle all of these electrons, every one of these 16, 32, 64, blah, 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 however many states I have in my quantum computer, they're all completely separate. They're all completely separate states. And I can process them one by one through a quantum machine that takes a quantum state and transforms it. Now, the cool thing about this quantum machine is that it works on all states at the same time. So say that I have, say, 32, okay, 32 quantum bits, qubits. How many different results can I get? Well, I've got 4,294,967,296 different states.
That's a big
Okay,
number.
it's a big number. Now I apply a quantum transformation to my entangled electrons, and this quantum transformation is working at the same time on all of 4,294,967,296 different states. It's a lot of computing that happens instantaneously. Whereas in a real computer, if we had to process 4 billion states, we would have to do the math, or we would have to run the function 4 billion times. A quantum computer with 32 quantum bits can perform 4,294,967,296 processing steps at the same time in one go. Now, what happens if I increase the number of quantum bits? My computer becomes tremendously more powerful. Look at 40 quantum bits. 40 quantum bits, we are in the quadrillion range. Billions would be 10 to the 9 trillions. Okay, we are in the trillions. Yes.
Actually, two. So one, do computers this powerful exist? And if they do, what's their use?
So quantum computers exist, and I don't know what the record number of qubits is. I think Google has the record at this point, and I think I recall about 60. Let me show you what 60 means here. Okay, just for the fun of it. We're talking about a billion calculations happening at the same time. It's like having a billion core computer.
So they use it for like big search engines like Google, so it could do multiple things at once. Well,
it can do billions of things at the same time. Now, the problem is quantum computers are not reliable at this point. So I don't know that they're used for anything other than scientific research on the functioning of quantum computers. That's my latest news from the quantum computing world, that they are tremendously powerful, but not quite ready for prime time. I've also read an article, actually a series of articles about an American company, and I forget their name. They're not one of the, famous Silicon Valley companies. They're sort of a traditional American industrial company that has built a very large and very powerful quantum computer, and they think it's ready for prime time, and they are, renting it out to the federal government for all sorts of applications. I'm not sure where we stand. I just want to show you how the power of a quantum computer grows incredibly fast with the size of the quantum computer. Now, you really have to think of this as the number of cores. We talked about cores in one of the very first lessons. How many cores does your computer have? My computer has 4. Okay, a quantum computer with 60 qubits is like a computer with 1.1 billion cores. That's kind of a large number. Okay, so that is the end of my presentation on quantum mechanics. I will happily take any questions, and otherwise I will give you a little bit of a break, and then we move on to more traditional topics in theoretical computer science.
I think we hurt our brains too much, so we can't really ask questions.
I thought
I'm
it
sorry
was
about that, Shari.
interesting. I thought it was really interesting.
Can you give me a sense for what the age range is on this call and what classes you're taking in science and math?
In
I'm
math, I'm in 7th grade and I take algebra.
I'm in
Okay.
6th grade and I do Excel math, so I'm not really sure what regular 6th graders do.
Okay.
8th grade geometry.
Okay.
7th grade algebra.
7th grade algebra. Okay. So I'm guessing you 9th grade algebra 2. Okay. I'm getting a sense that you guys weren't expecting to delve into quantum mechanics, before the end of the school year. Well, lo and behold, you did it. How incredibly complicated was this stuff?
Very.
It was
Okay.
interesting but complicated.
Yeah. I do want to point out that the most complicated math I've shown you is this, okay, which is really just the distributive property of multiplication.
Can you put these slides on the agenda doc?
Absolutely. How do I do this? Public. Shall we get started in 3 minutes?
Sure.
Sounds good. So I decided to try and pick up some machine learning concepts. And so I started working on this Coursera course, which revises linear algebra and then does a bunch of matrix manipulation stuff in MATLAB.
Is that Andrew Ng's class?
Yeah. Have you done it?
Yeah, very nice.
It's pretty cool, actually. Yeah. And then I started trying to code in Octave on a Mac, only to realize that it's a disaster. And so after wasting 3 hours, I switched to MATLAB online, and that's going a lot better, but it's just been painful, really painful.
Yeah, Octave is, not one of the most numerous communities out there, and so it's not as well. There isn't as much development going on Octave as there is, for instance, on
R,
Python, NumPy. R is very, very old. It's a very, very painful language. I would not recommend it. There's some wonderful algorithms written in R, but writing your own stuff in R is excruciatingly painful. I'll get started. We have lots of other fun stuff to get you ready for your PhD dissertation in computer science. So I'd like to ask you a question. When do you think computer science was born? And when were computers first built? Let me ask it differently. What do you think came first, computers or computer science?
Computers.
Computer science.
I'm hearing a bit of both. One would say, well, it would make sense to have the computers first, and then once we have the computers, we ask ourselves, well, what can we do with them, and how do they really work, and how can we make them better? So let's build a science around them. Turns out that mathematicians were studying the science of computation well before computing machines were actually available. And so in the 1920s, the founding fathers, or two of the founding fathers of computer science, Alan Turing and Alonzo Church in England, were working on the theory of computation, which eventually developed into computer science. And they were asking themselves questions that we would hardly recognize as questions relating to computers. They were asking themselves questions such as, does the theory of general recursive functions, which is purely mathematical theory, is it equivalent to the theory of formulas expressed in a language called the lambda calculus? And they were able to prove that these two ways of expressing mathematical formulas and expressing, ways of performing math were equivalent. Every time you had a recursive function written in the language of recursive functions, you could translate it into a lambda function and vice versa. And again, these were mathematicians, right? Pure mathematicians. So Church, the professor, Alan Turing was a student, the professor came up with this general idea. He said, I've proven that these two ways of doing math, one with lambda calculus and one with recursive functions, are really equivalent. Every time I write, a formula one way, I can always translate it into the other way. It must be, and these are very powerful theories, right? There's all sorts of theories that are less powerful than this, where you can always translate from the less powerful to the more powerful, but there are examples where you cannot translate from the more powerful to the less powerful. And so he said, I'm kind of thinking that these are the maximal computation theories, the maximal theories of computation. There's nothing more powerful than either recursive functions or lambda calculus. And Alan Turing said, well, this is kind of very, very theoretical. We should think in terms of what real computers will be when electrical engineers will have enough technology in their hands to be able to build them. So let's imagine how a real computer could be built, and let's try to work out how a real computer would process recursive functions, how a real computer would process lambda expressions. And let's see whether a real computer, which again, they didn't really have, so they were imagining one, and they were sort of doing the math, with paper and pencil, or blackboard and chalk, imagining what the computer would have done. Is the real computer more powerful than lambda expressions or recursive functions? And so Alan Turing came up with an idea of how a real computer might look like. And he said, well, a real computer is going to have some electrical switches. Today we call them transistors. He didn't have transistors at the time, so he had switches. And it will have a tape. They also did not have tapes at the time, but he imagined that a computer would have a tape, and it could write messages on the tape, and it could read messages from the tape. And he says, real computers will have a finite amount of tape. They will have, I don't know, a tape where they can store 1,000 pieces of information. Maybe they can store, 10,000 pieces of information. But then, the tape comes to an end. But that's not part of the theory. He says, I can always imagine putting a bigger tape or a bigger tape reader. Okay, so let's imagine that we have infinite tape. What kinds of things could we do with a computer that has a certain number of switches, say 12 switches, 15 switches, 7 switches, and a tape that's however long it needs to be? That seems like a very simple description of a computer, right? It's about as simple as it gets. And obviously you can wire the switches differently. He was actually imagining like electric switches where the switch itself is controlled by electricity. There are real switches, like for instance, you guys probably have seen Alexas and Google Homes and so on turning on and off the lights in your home. The way they do that is they have an electrically controlled electrical switch. Okay, so no magic there. He was imagining some of these electrically controlled electrical switches that an electrician could wire however they needed to be wired. And then he could hook up these switches to a tape machine that could read and write one piece of information to the tape, and then it could cause the tape to rewind or go forward by one step. And guess what symbols he was imagining to write on the tape? If you guessed binary, you would have guessed right. So he was imagining that the tape could only store zeros and ones. And so he didn't actually have switches. He didn't really have wires. He didn't have tape readers. He just imagined this and figured out on a whiteboard or blackboard at the time how his Turing machine would work. And obviously there are infinitely many Turing machines. You can provide a different number of switches and you can wire them differently. And so he asked himself the question, given enough switches, can I build a machine with switches and a tape that will do whatever math calculation I can write using the theory of recursive functions? Or can I build a Turing machine that will compute any lambda expression? And his, the Nobel Prize for Computer Science, is named after him because he came up with the first proof, theoretical mathematical proof of the equivalence of a quasi-real computer, something that could actually be built with technology that was mostly available at his time, and purely mathematical formalisms describing computations. Now, he didn't prove that any computer would be equivalent, that any computer could do the same things. He just had one type of computer, the Turing machine. And he showed that the Turing machine could compute anything that could, any formula, any math that could be written using the language of recursive functions, or any math that could be written using the language of lambda expressions. He also proved the opposite, right? He proved that he could write a recursive function that did whatever math the Turing machine that he was imagining was programmed to do. Given a Turing machine with a certain number of switches wired in a certain way, he could always come up with a recursive function that produced the same result. He could always come up with a lambda expression that produced the same result. And so he extended his teacher's hypothesis. Alonzo Church had said, well, I think that any mathematical formalism that we can come up with is going to allow us to write the same mathematical formulas or equivalent mathematical formulas. We cannot build anything fundamentally more powerful than recursive functions or lambda functions. And Turing said, turns out that even computers are equivalent to these theories. I can imagine a computer that can compute a recursive function. I can imagine a computer that can compute a lambda expression, and I can go the other way as well. I can't really build a computer that does anything that cannot be done using the purely theoretical mechanisms that Alonzo Church was studying. So they came up with let's call it the glass ceiling of computer science. It's called the Church-Turing Thesis. Okay, Church-Turing Thesis. I'll show you the Wikipedia article. We will not get into the detail, but basically the Church-Turing Thesis is there is a limit to what computations we can actually write and run on a real computer. Even a real computer that doesn't exist yet. Any real computer. Okay? So this is very important. This sets the upper bound to the power of our technology. It even sets the upper bound to the power of our theory. It says, even in theory, there are things that we cannot solve. There are problems that we cannot solve. That we cannot solve with computers. And we could solve them by, I don't know, by going to a psychic and asking them, what's the answer to this question? And he tells you the answer is 42. And lo and behold, you've got the answer. But you can't actually find the answer. You can't find it with a computer. You can't find it with paper and pencil. You can't find it with any deterministic way. You can't find it in any way where you can actually follow a list of steps and sooner or later you'll get the answer. That's the incredible result of our best buddies, Turing and Church. And this is also a very significant result from the perspective of guiding our understanding of computer science. Computer science is largely about what can be done and what can't be done. Turing gave us a limit on what can be done. He didn't tell us how long it'll take, but he told us certain things just can't be done. Let me give you an example of something that can be done and something that cannot be. And bear in mind that these guys didn't have user interfaces. They didn't have Chrome. They didn't have monitors. They were just imagining a machine to do math. Okay, that's it. So, you can build fancy UIs. You can build, always better UIs. But in terms of the foundational math that you can do with a computer that is at the heart of everything, there's a limit. Here's a thing that a computer cannot do. A computer cannot tell you whether a given other computer working on a given program is going to produce the right result. That's interesting. Okay, it's kind of a difficult question to imagine. Imagine you have a Turing machine or you have a real computer and you have a full description of how it's built and you have a description of the software that it's running, which in the case of the Turing machine means how the switches are connected to one another. And you want to know whether this computer will produce the right result. Maybe you know ahead of time. Well, obviously you need to be able to know whether a result is right or not. Okay. Question is that computer going to produce the right result? There is no general solution to this problem. Now, on any particular run of a computer on a given program, it's either going to give you the right result or not. So I can say, well, I think it's not going to give me the right result. And I could be right or I could be wrong. If I'm right, I'm right. But I cannot build an algorithm that will make me be right all the time. I have to take a guess, basically. That's what it is. I have to take a guess, and sometimes I'll be right, sometimes I'll be wrong. But there is no way to know for sure in all possible cases. Now, it's important that there are, that we set these limits to what we can do with computers, because this guides our intuition, not only for computer science, but really guides our intuition in the theory of what is doable and knowable by humans. There's an incredible depth to this result that I'm having a hard time conveying. It's kind of like Einstein saying the maximum speed you can achieve in the universe is the speed of light. Under no circumstances can you ever do anything better than that. Alan Turing's result has the same significance as Einstein's speed of light as the limit of, like the speed limit of the universe. Okay, so now let's focus on the problems that can be solved with computers. Okay, when we can solve a problem with computers, we have to write a program, or we have to build a Turing machine, if you will. Or we have to build an algorithm, which is a sequence of steps that we will go through to solve the problem. Algorithms use resources. What two resources do algorithms use? They use space, RAM, or in the case of the Turing machine, they use a certain amount of tape, and they use time. Say that, I want to search throughout every web page in the world for, all the web pages that talk about pizza. I'm Italian, I like pizza. I want to figure out what websites talk about pizza. Well, that's a problem that we can solve. It's solvable according to the Church-Turing Thesis. So how can we solve it? Well, one algorithm that can and will eventually solve this problem is to go through all the web pages in the world, one after another, one word after another. And every time I see the word pizza, I take the web page and I take a copy. And I add it to my result set. And I go through billions and billions and billions of pages. And because pizza is a fairly common term, I will find millions and millions and millions of pages. This is an algorithm that, from Turing's perspective, works just fine, right? It will eventually produce the right result. But it will take billions of years on a single computer, and it will require more RAM than any single computer has. Hang on. Okay, so it's an algorithm that solves a problem, but it doesn't solve it in a reasonable time, and it takes too much space. So we need better algorithms. Turns out that Google has a better algorithm. It's based on inverted indexes, and Google is able to find all the solutions to the question within 200 milliseconds. So you can have algorithms that will take billions of years to solve a problem for which the best algorithm will take 200 milliseconds. That gives you an indication that computer science needs to understand how algorithms use resources to achieve a certain result. Okay? And we need to study in a formal way, using mathematical theory, the resources that are consumed by a given algorithm. So certain problems can be solved in a constant time. We've used JavaScript to read colors out of pixels, right? Reading the color of a pixel, according to our friend Ms. Taylor, takes a constant time. This I will, with some approximation, it'll take always the same amount of time. So yes, we could go through all sorts of other pixels prior to getting the right one, and we could spend a lot of time doing useless things. But fundamentally, if all we need is the color of a pixel, we can get that pixel and read its value, and that's it. Okay, so it doesn't have to take a long time. She's also giving examples of things that you're not doing with a computer, you're doing with yourself. Your brain requires a certain amount of time per page that you need to study for an exam. So if you need to study, a book with 100 pages for a given exam, it'll take you some amount of time. If for another exam you need to study 200 pages, it'll take you roughly twice as much time. This is called a linear problem, a problem where you need to go through a certain amount of input, and you cannot find the solution without looking at all the input, but you really only need to look at the input once or twice, not more, and then you have the solution. Some problems require more than linear time. This is actually a bad example, so I'll not use this example. There are problems where you may need to process one element at once for every other element in the input. And I will give you an example. Say that sorting. Sorting is ordering elements in according to some ordering. For instance, I might be ordering numbers from the smallest to the biggest, or I might be ordering text according to alphabetical order. Say, ordering the names of the students in this class. One way to do this, they're providing this example, which is really stupid, which is to pick elements at random and then check whether they are in order. If they're not in order, try again. I will not even call this a real sorting algorithm. This is a real sorting algorithm. This is called insertion sort. You start with an empty sorted list, and you start with a big not sorted list. You look for the smallest element of the not sorted list, you pick it out, and you put it in your sorted list. And then now your sorted list has a length of 1, your not sorted list has a length of n-1. And you repeat that. So you look for the smallest element in the not sorted list, you pick it out, and you put it in your sorted list. And then you do it again. So every time you look for the smallest element in the list, you are processing all the elements in the list. And you need to do this for every element in the list. So you're basically doing n squared. You're inspecting an element n squared times. Okay, this is a polynomial complexity. It's a polynomial with degree 2. There are problems where you may need a higher degree, like third degree polynomial, fourth degree polynomial. These polynomials can get pretty bad pretty quickly, but still they're considered doable. Then we have problems where the number of steps the algorithm needs to take grows even faster than any polynomial. For instance, they grow exponentially. Imagine having to find the right password to get through to log on to a website if we don't know the password ahead of time. And say that we know that the password is of a certain length. For instance, the password is a 64-bit number. Well, the size of the problem is 64 bits. How many guesses do I need to be able to get in? Well, I need to do no more than 2 to the 64. If I had 128 bits, I would have to do 2 to the 128 guesses. That's an exponential growth. It grows very, very, very fast. Theoretically, problems that are exponential are solvable from the perspective of the Turing machine, from the perspective of lambda calculus and recursive functions. These algorithms are real algorithms that can really be built into a computer, and so these problems are solvable. But it might take longer than the age of the universe to solve these problems. So they are theoretically solvable, but in practice they may not be solvable. Okay? And so there's a distinction between what is theoretically solvable and what is theoretically solvable but practically not. And that brings us to the question that I proposed at the beginning of class, whether P is equal to NP. I'll give you I'll try to give you an example. So we talked about the problem of finding the correct password. That problem is not polynomial. P stands for problems that can be solved using a number of steps that is some polynomial of the size of the input. So finding the smallest element in a list, linear time, the polynomial is degree 1, not a problem. Ordering a list, I gave you an example of a way to do that using n squared steps. N squared is still a polynomial, no problem. It's a polynomial. Sorting is a polynomial problem. Finding the password, however, is not polynomial. Okay, we cannot do that in polynomial time. Unless we know something about what the password ought to be, we can't solve it in polynomial time, we just have to guess. And the number of possible guesses is exponential. Turns out that that problem can be solved in polynomial time using a non-deterministic machine. A non-deterministic machine is one that can basically spin up any number of cores. It has infinitely many cores available to it. Okay, and it can do lots of things at the same time. But the number of cores can only grow polynomially, right? It can't spin up infinitely many cores all at the same time. So problems like finding the right password can become polynomial on a machine that has infinitely many cores and that can spin up new cores on an as-needed basis. Those problems are called NP. They are non-deterministic polynomial, okay? Non-deterministic polynomial problems are hard to solve. They're really hard to solve. But there's at least a theoretical model in which they could be solved in a realistic amount of time if we had some really, really cool technology that doesn't currently exist. Now, what we don't know from a theoretical perspective, we don't know yet from a theoretical perspective, is whether non-deterministic polynomial problems are really any more difficult than regular polynomial problems. In other words, are these two groups of problems really different? Now, we have all sorts of non-deterministic polynomial problems that are really, really difficult to solve, but we don't know whether they're difficult to solve because we haven't found a better way. Now, if we can find a better way, then it turns out that these non-deterministic problems, non-deterministic polynomial problems, just become regular polynomial problems. But nobody knows. At this point, nobody really knows. So this is an open question in computer science, and it's the biggest open question in computer science. Can we build algorithms that can solve non-deterministic or non-polynomial, non-deterministic polynomial problems in polynomial time using regular hardware? If you guys can solve this question, Nobel Prize awaits you. Okay. Now, what happens if we end up discovering that P is really equal to NP? In other words, what happens if somebody here on this call goes on to be a computer scientist and builds an algorithm to transform NP problems that are difficult but maybe solvable into P problems that are just solvable, that are a piece of cake? Turns out that encryption would break. Why? Because a lot of the encryption technology that we have today is based on problems that are easy to set up. So setting up the problem takes P, complexity, but breaking down the problem takes NP. And I talked about, asymmetric key cryptography, private keys and public keys. And I told you, if you have the private key, theoretically, you could reconstruct the public key. If you have the public key, theoretically, you could reconstruct the private key, because the keys have to be in a one-to-one relationship. So if I have one, theoretically, from Turing's perspective, I can write an algorithm that gives me the other one. But in practice, I can't, because finding the other one is an NP problem. Finding the second key from the first is an NP problem. Now, if somebody here on this call wins the Nobel Prize for Computer Science by discovering that NP is really the same thing as P, and building an actual algorithm to transform NP problems into P problems, then encryption using today's asymmetric keys, today's private keys and public keys, breaks, because anybody would have software that could translate a private key into a public key and a public key into a private key. That's not fun. So more powerful encryption techniques that are not assuming that P is really not the same as NP are being developed. Not only that, but encryption techniques are being developed that are resistant to quantum computers. I also told you that quantum computers have incredible amounts of power, and they will be able to break all sorts of encryption techniques that we have today once they become sufficiently reliable. And so we are definitely going to see a lot of our private keys be retired over time in the next few years, really, as quantum computers come of age. So we need better encryption, right? We would also be able to optimize a lot better. What does optimize mean? Optimize is when we use a computer to find the best possible solution to a problem. Sometimes, finding a solution is easy, but finding the best one is really hard. Imagine that I'm an airline and I have to decide how to route my airplanes and which airports to connect at what time. I can make all sorts of decisions, and I can easily create a network of flights that connects all the airports. But what is the set of connections that maximizes my profit? That's really the question that I want to ask. That's the kind of question that computers are, well suited for. But a lot of optimization problems are in the NP world. And so to really be able to solve them accurately, we need either more powerful computers, but infinitely more powerful computers, or we need better algorithms. Now, proving that NP is really the same as P would allow us to build those more powerful algorithms. And better transportation layouts is essentially an example of better optimization. Okay, what else do I have here? So the three themes for tonight are quantum computing, quantum mechanics, okay, which I presented. The second one is what is theoretically feasible using computers? And that brought us to Turing and Alonzo Church and the Turing-Church thesis that says that there is a maximally powerful computing formalism, a maximally powerful computer, and that there's many ways of building maximally powerful things, but they're all the same power. Turing machines and regular computers and recursive functions and lambda calculus and all sorts of other techniques all result in the same amount of power. Okay, that's the first big takeaway. And the second big takeaway is, among all the things that are theoretically possible, some are practically possible and some are not practically possible. And some are just not doable, even, in other words, they're even outside of NP, right? So some problems are just so difficult that, yes, theoretically, if we had infinite time, we could find the solution, but there's really no real hope, okay? But there's a lot of interesting problems that are on the brink of being doable. And we call these problems NP. And we don't really know whether they really are more difficult than the regular problems that we can solve with a regular computer. I have shown you all of the theory that I intended to show. I have a little puzzle for you before I leave you, but I want to take questions first. Okay, no questions. You guys are ready for your PhD dissertation, ready to defend your PhD dissertation. So let me tell you about one of the little nooks and crannies of computer science that keep computer scientists chuckling for days and days upon end. They're called quines. A quine is a program that has a very, very useful now let me reformulate it. It's a very, very useful program whose purpose it is to produce its own source code. When you run a quine, the program produces itself. Okay, how cool is that? Now, is that really useful? No, of course not. No, nobody would ever want to buy a program whose only output is the program itself. But it's really cool to learn to write a program that produces itself, and it's not easy at all. Okay? Can you guys come up with a quine in JavaScript? Let me show you an example of a quine in Bash. Can you guys see my screen?
Yeah.
Okay, so I'm writing one of the most interesting quines in the history of computer science, echo $bash command, which produces echo $bash command. This is a one-liner in Bash that produces itself on the output. Okay, I'm really cool. I'm thinking that I must be a genius for having written a quine in Bash. And I'll be very proud of myself for the rest of the evening. Now, can you guys, based on your knowledge of JavaScript, can you guys write a quine in JavaScript? And there was a question. Somebody was asking a question. Hello, hello? I hope I haven't scared you guys. Today was a tough lesson, some really tough material. It's really just it's an opportunity to see what's out there, what computer science is about. And hopefully it'll get you interested in these topics, and a few will end up studying these things in college, and hopefully someone will earn the Nobel Prize for Computer Science, which is called the Turing Award appropriately, and will invite me to the celebration. Will invite us, Sanjay too, of course. I am done for today, and proudly, only a minute late.
Yay.
Okay, so what do you guys want to do for tomorrow? Do you guys want to go through everything all over again? There was, I think, another section. Let me just take a look at the final review and tell you guys if it was worth. I think you can stop recording now, Alex.
Okay.
Yeah, I mean, I